All right, so second video for today, we're going to be looking at limits as x approaches infinity. Now, the reason for this is because this is going to help us with when we're looking at asymptotes. It's also going to help us just looking at in behavior and things like that. So let's go ahead and consider this problem right here. X approaching infinity always makes things a little bit more interesting, or negative infinity, of course. The thing to remember is that infinity is actually not a number, it's an idea. It's the idea that you can make it as big as you want, or even bigger than you want it to be. Or if it's negative, it can be as big as you want with a negative, or as even bigger than you want it to be. And so the big thing here is that we recognize that for any constant, as we approach infinity, x is going to be a lot bigger than any constant, right? Because if x is infinity, it's, if x is a billion, it doesn't really matter what c is. If it's a lower constant, it's going to be a lot smaller than that x. If you say that the constant, well, what if the constant is a billion? Well, x approaching infinity, that could be a billion billions, or a billion 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 billions, so a Google billions, I don't know. So recognize that as x approaches infinity, x is going to be a lot bigger than c, which follows then that x squared, if I take that really, really big number and multiply it by itself, so I have a Googles, right? That just kind of, obviously the x squared is going to be so much larger than x. Same thing as I go up. And so anytime that you have x to an exponent, it's going to be much, 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 much larger than anything before that. So for example, anytime I take c and divide it by x, as x approaches infinity, this is going to be 0, right? Because x is going to be huge. This is like taking a 5 and putting it over, I don't even know what that number is, but there's a whole bunch of them. It's going to be a really, really small number, which is going to be essentially approaching 0. Is it 0? No, but that's not what the limit is asking for. The limit isn't asking for the actual value. It says what happens as x gets bigger and bigger and bigger and bigger. So we're going to use that idea. I'm going to show you two ways that we can find the limit as x approaches infinity. Now, my preferred way is to look at the variables and find out which one has the highest exponent, and then just divide all of them by whatever has the highest exponent. If this were an x squared, I would divide everything by x squared. Since the biggest one is an x, then all I'm going to do is I'm going to say, okay, let's divide everything by x. So 2x divided by x is 2. 3 divided by x would be 3 divided by x divided by x over x is 1, minus 4 divided by x. Now, this simplifies things a little bit, because up here I had 2 times infinity plus 3, and I had infinity minus 4. That gets a little bit difficult to work with. But once I've written it this way, it has now been simplified, because following the limit rules from the previous video, I made you write them all out in the previous video. Now I'm just going to assume that you know the rules and that you can do them individually. And so we're going to say, okay, well, the limit as x approaches infinity of a constant is still that constant, right? It's not affected by x. And then plus 3 divided by x, well, if x is infinity, 3 divided by infinity is going to be essentially 0. And then I'm going to have 1 minus 4 divided by anything really, really big is going to be getting closer and closer to 0. Notice I don't have the limit anymore, because I've actually done the limit at this point. And then, so that'll be 2 over 1. So there we have that the limit was 2. Now, many of you knew that already because of the shortcut we learned last year, which is where you essentially take that and you cover up, I just covered that up with my finger, that doesn't do it again. Cover up the x's, which leaves you with the 2 over 1. Now, so this actually kind of proves that idea. This is why that actually worked before, because we're taking the biggest x value and dividing everything by that, which ends up making it work out. So now let's apply it. We have a problem. It wants us to find and discuss all the asymptotes. All right? So the first thing that we're going to do here is we're going to factor it. Okay? Factoring is going to help, because that will give us an idea. We're going to have to find the asymptotes anyway, which means we need to find when the bottom is 0. And so we're just going to factor the whole thing. All right? So we're going to take the top. We're going to rewrite it as f of x equals x. That we're going to factor. That's what I just said. So x and x. It looks like it needs to be minus 2 and minus 1 all over 1 minus x, 1 plus x. All right. Now, the second thing we're going to do is, if we can cancel anything, we will. All right. because that's going to simplify it later. Now, you may say, well, I don't think I can cancel anything. But you'll notice that if I rewrite it this way, if I factor out a negative and make this negative x plus 1, that's the same thing as 1 minus x, which is now over 1 minus x and 1 plus x. Okay, now this, because of the 1 minus x and 1 plus x, remember we get the discontinuities when the bottom is 0. When the bottom is 0, that's when we get the problem because it's undefined. And so at x equals 1 and at x equals negative 1, there are discontinuities. However, this one right here will cancel out. Now, we did see that before in the first video. We saw the x's cancel out on the top and the bottom. This means that we're going to have a hole at x equals 1. Okay, so the hole is actually not an asymptote, so we're not actually going to have to worry about it. All right, so now that I've identified that one of the two discontinuities is actually the whole discontinuity, it's not a asymptote, we can go ahead. I'm going to suggest that we do a sign diagram. Okay, and so let's do a sign diagram. Now for the sign diagram, we need our asymptotes, and we need our discontinuities, and we need our X-intercepts. And so we've already found that we have a asymptote, a vertical asymptote at x equals negative 1, because this one was the vertical asymptote, that one was the hole or the discontinuity. And so at x equals negative 1, that's my vertical asymptote. So I'm going to make that dash. At positive 1, I've got a hole. So we're going to mark that one, but we're just going to mark it with a little hole there to show that the graph continues. That one would actually converge. If we were to find the limit as x approaches 1, we would actually find that it would converge at that point. You would plug in the 1 for x, and you could actually find out what it converges to. All right? Now, just give the rest to your sister. No, not your sister, your sister. All right, here we go. Just put it on the table. So at this point, we need to find the x-intercept. So the x-intercept, well, if you make the top 0, right, that's how we're going to find the x-intercept. Well, one of them was at 1, but we already know that's a hole, so it's not necessarily an x-intercept. The other one is at x minus 2. And so x minus 2 equals 0, so that means we've got an x-intercept at 2. All right, so there's our sign diagram. If we plug in a couple of numbers, easy numbers to work with, maybe 0. So I put in 0, 0, so I've got 2 over 1, so at 0 it's positive. The discontinuity will not cause a sign change, and so all of this will be positive. There should be then a switch on this side and a switch on that side, so negative on both those sides. Now this helps us out significantly because at the vertical asymptote, let's go ahead and talk about the vertical asymptote here. At x equals negative 1. So as x approaches negative 1 from the left, we see that you're going to have a negative value, which means that f of x will approach negative infinity. We already know it's an asymptote, and since the values are negative here, that means it's got to be going down. Okay, it switches, which means it's going to be going up here. And so as x approaches negative 1 from the right, so as I go this way, I go up to positive infinity. So f of x approaches positive infinity. All right, so we've done that very easily and talked about what's happening at the vertical asymptote. Now the last thing we want to check is there a horizontal asymptote? All right, so if we look for now a horizontal asymptote, remember the horizontal asymptote is where we're going to say, okay, what happens as x gets really, really big? Is there something that it's going to be approaching and getting closer and closer to? And so we're going to come down here and we're going to do the horizontal asymptote, which means x approaches infinity. Or you can do x approaches negative infinity. It doesn't really matter. But infinity is usually easier to work with. So we'll go the limit as x approaches infinity of x squared minus 3x plus 2 over 1 minus x squared. Now again, my preferred method of doing this is to divide everything by whatever the largest variable exponent is. So that would be the x squared. So I'm going to divide everything by x squared. x squared divided by x squared would be 1. If I take 3x divided by x squared, that will be 3 over x. And then if I take 2 and divide it by x squared, I'll have 2 over x squared. Take 1 divided by x squared, and then minus, and x squared divided by x squared is 1. And so now when I take the limit, I can take the limit of each of these pieces individual, right? Because I can take the limit of a constant, I can take the limit with the subtraction, with the addition, with the division. So limit as x approaches infinity of 1 is 1. This, of course, will go to 0. This, of course, will go to 0 because I'm dividing by humongous numbers. All over 1 over x squared is also 0. Please notice that I'm putting the zeros down. That's because I want to make sure that when I get to the end, I don't make a mistake. So this is 1 minus 0 is 1, and then 0 minus 1 is negative 1, which means there is a horizontal asymptote at negative 1. Yes, that is the fire. Thank you. All right, so horizontal asymptote at negative 1. X equals negative 1, of course. Now, with that, I can now look at the end behavior. So as x approaches infinity, f of x approaches. Now, it's approaching negative 1. And since we've got, let's see, the graph is coming from the top here. It goes down, down, down. And then at the x-intercept, it crosses over. Sorry, that was really sloppy. Let's go ahead and get rid of that. So it should go something like this, positive, 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 and cross right there. So if we're approaching negative 1, here's my asymptote. That means it should be approaching from the top, right? And so I'm going to say approaches negative 1 from the top. And then as x approaches negative infinity, f of x should approach negative 1 from the bottom. Now, you can use these signs if you want. Notice I use those up here as well for the left and right. Or you can just say as x approaches like negative 1 from the left, as it approaches from the right, and then it approaches top, and it approaches bottom. Okay, either way is fine. I prefer the symbols. I'm a math symbol guy. But if you prefer to use the words, that's fine too. All right, well, that's it. That's how we would discuss all the asymptotes. We could obviously go and then sketch some type of graph if we wanted to rather quickly. We could go, here's my vertical asymptote at y equals negative 1. Here is my, x equals negative 1, sorry. Here's my horizontal asymptote at y equals negative 1. I think I messed that up earlier, so the horizontal asymptote is at y equals negative 1. And then I've got an x-intercept, of course, out here at 2. And so then I would just kind of sketch it and go like this. Remember, at 1, I've got to have a hole before I cross over. And then out here, obviously, it would look something like this, and that would fit in with all the things that we found. All right, that's it. Ciao.